worse, and I like what she's saying.
Do it early.
Uh-huh.
All right.
We were supposed to go over with Monday on is how to do the lab dynamics. That's what I was like, I don't want to do a bunch from.
Y'all set your lab lecture yet?
Yeah, we had one.
Yeah, you had one.
It was just another syllabus.
What'd you think?
It was good. It seems like it's going to be fun.
He's teaching us how to do the lab report, not the pre-lab though.
All right. Sorry for the late start here.
It's actually way better to track, supposedly. Or like,
Oh, please tell me.
in my experience.
Is this the right lecture? Or did I not copy over the? Oh, thank goodness. Yeah, crap. Did I not? No. Yep. All right. Well, volume on this is turned off. I think I didn't. Can someone on the Zoom call verify that this thing's recording? I don't know if
Volume's working. Morning.
Okay, yeah, you're right. There it is. There's the thing on the top left. Thank you.
Oh, yeah, look at
that. Yeah, sorry, the volume's turned off here, right? Normally I know because when you log into it, right, like this meeting is being recorded, right? And I didn't hear that because they turned off the volume in the room, I guess, on the computer. So, anyways, and I apologize about getting a minute late here, but let's get going. Talking about reaction mechanisms. Okay, talk more about this. I uploaded videos for next week where we'll be doing stuff with steady state approximation, pre-equilibrium approximation, and all that wonderful stuff. And we'll spend plenty of time doing plenty of examples on those wonderful things. But yeah, so today, talk more about reaction mechanisms. Any questions about anything before we get started, right? Wednesday next week, the first homework is due as well. Yeah, any questions from anybody? Let me try to move where this thing is so I can see something if someone asks something in the chat. But yeah.
What did you say it was Wednesday next week?
The homework, I believe.
Okay.
I mean, whatever the syllabus says is when it's due, but I think it says it's due next week, right? Wednesday, the first homework. So, right. Problems 2 through 13. Problem 1 is free points. Doesn't exist. I guess I was told I was labeled it incorrectly. I had someone comment the other day about not being able to access the files or something like that. Is that change different, or are people able to like go into the? I know some people don't open up the files folder for the classes. For me, I online. Are people able to go into the files folder and see the homework from there, or do they have to get the homework through the link? Nope, you still can't.
You have to go through the files. You can't go through the assignment.
Oh, wait, you can't go through the assignment. You have to go through the files?
Yes.
Is what you're saying? Okay. Okay, so people can get it in the files tab. You just can't get it like through that link in the assignment. Apparently that link's busted. Fantastic. Great. Yeah, they changed up some things on Canvas over winter break.
It's been fun.
In terms of tools and stuff like that. Yeah, just your water bottle or? Yeah. Yeah. There you go. Yeah, so they changed up some stuff in terms of kind of the administrative tools and how things look and work and whatnot. And so I will try to fix that link on the assignment. But people can go into the files tab and at least get it, right? It's just the link is no good. All right, fantastic. Okay, so let's get going. So, right, we talked kind of about some of this stuff at the end of the lecture last time, right? Defining an intermediate, catalyst, right? Elementary steps and reaction mechanisms and things of that nature. Okay, right, talked about some of these questions, okay? And so we finished up and stopped right before we're gonna start talking about the rates of elementary reactions, okay? And the rate laws. So, right, when we first, introduce kinetics and talk about rates of reactions and rate laws, right? We always say, well, the rate law is some form, rate constant times concentrations and yada, 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 right? but we say, but do not use the stoichiometric coefficients in those reactions to write out the rate law, because it's maybe not necessarily the actual rate law, right? That's not true for elementary reactions. So if the reaction is literally, as the reaction is written here, H plus Br2 colliding together in space, right? So you imagine H and Br2 collide together in space to form HBr and Br, okay? That rate law for that reaction is going to be the rate constant. I should have put K1, not Kr. That rate constant times concentration of H times Br2. Let me just change that, just doesn't bug me. All right. Right. So it's going to be, right, again, the rate law for that reaction is going to be K1 times H times Br2, right? Because that is what's happening at the molecular level, right? It's H and Br are colliding together, right? Which means that how fast that reaction occurs depends on the concentration of H and the concentration of Br2. It has to, because both of them have to be there and have to collide to hit for that reaction to occur, right? And as you increase the concentration of H, you should increase the rate of the reaction, because now you got more hydrogens flying around, bumping into bromine molecules more frequently, right? Just like if you increase concentration of the bromine molecules, those things are flying around more frequently and bumping into the hydrogens, right? And so you should have that dependence in your rate law based off of their stoichiometric coefficients in the chemical reaction, right? But again, this is only true for elementary reactions, right? Because elementary reactions, right, are ones that describe what is happening at the molecular level, right? For a general chemical reaction, right, as, you know, say, oh, I don't have it here, right? But the reaction, I had it somewhere. Okay, I don't. The reaction like H2 plus Br2 going to 2HBr, right? That reaction, H2 gas plus Br2 gas forming 2 hydrogen bromides, 2HBr, right? That reaction is not taking place with how the chemical reaction is written, right? It's not two hydrogen molecule, a bromine molecule bump into each other and say, hey, let's switch partners, right? And a hydrogen grabs onto a bromine and the other hydrogen grabs onto the other bromine, right? And they break up with each other, right? It's not some sort of swingers event or something like that going on, right? That doesn't happen at the molecular level, right? And so the rate law for that reaction, right, isn't going to necessarily be just the rate constant times concentration of H2 gas times concentration of Br2 gas, right? Because how the reaction is actually occurring might not depend that much on the actual concentration of H2, might not depend that much on the actual concentration of Br2, right? Or maybe it depends a lot, right? Because maybe the very first step in that reaction is 2 hydrogens colliding together, right, and to form, you know, I don't know, H3 and H or something. Yeah, I don't know, right? Like some random thing, right? And so maybe the rate of the reaction depends on the concentration of hydrogen squared or something, right? Like, so there's all sorts of things that could be actually going on at the molecular level that is different than what our overall reaction that we write tells us, right? And so that's, again, why for general chemical reactions, we can't write the rate law based off the stoichiometric coefficients of the reaction. But for elementary reactions, we can, right? For elementary reactions, it's okay to just read off the rate law from that reaction. It's the rate law is going to be the rate of the reaction equals the rate constant times concentration of reactants. That's it for elementary reaction, because those elementary reactions are what's happening at the molecular level, right? And again, we'll note, because this will be very useful as we go forward, right? Just again, keep in mind about the fact that the rate of your reaction is related with the rate of change of your reactants and products, right? Now, in this case, the stoichiometric coefficients of everything here is 1. So it's just negative the rate of change of H, negative the rate of change of Br2. It would equal the rate of change of HBr and the rate of change of Br, right? And that's going to be very key and very important as we kind of write things out. And we'll see that in even some of the next slides, right? To keep that in mind, okay? So... right, so here we have a question, right? Given this mechanism, what is the rate of change of the concentration of B? Okay, so what that's asking for is the derivative of the concentration of B as a function of time. What does that equal? Okay, I'm going to write this out, and I have the answers and things written on the slide, but I want to just kind of go through things in more detail. So I'm going to write out the reactions here and flip over to this, because this is something. Okay, so this type of question that we're doing right now here. Wrong button. I was like, the light's not turning on. Right. So this type of question, that autofocus make it worse. All right. So this question basically asking, what is the rate of change in concentration of something versus time? This is a question you're going to not necessarily be asked in every single problem related with reaction mechanisms and rate laws, but it is a question you're going to have to answer yourself as you try to solve the problem. Okay? Because often the questions will be, here's our reaction mechanism for this thing. What's the rate law? Does it agree with the experimental observation, right? That's the typical type of question you're asked when you see mechanisms. To answer those questions, we're going to have to answer these type of things, right? Because again, right, if we know what the rate of change of our concentrations are as a function of time, right, recall, right, that so the overall chemical reaction here, right, is 2A plus D going to P, right? That's the overall chemical reaction, okay? Right, the rate of that reaction, for example, is equal to the derivative of the concentration of P as with respect to T, right? That the rate of our reaction is just equal to that rate of change of the formation of our product, okay? So if I know what this equals, right, in terms of concentrations of other stuff, then I know my rate law, right? And so we're often going to be looking for what are the rate of changes of concentrations of reactants and products and intermediates in our reaction mechanism, okay? So let's try to answer this question. What is the change in concentration of B as a function of time, okay? So how many reactions does B appear in my mechanism here? I'm going to highlight the mechanism just to, right? This is my reaction mechanism, okay? How many reactions does B appear in? 2, okay? So I'm going to have 2 terms here in this mechanism, okay? Right? So it appears in 2 reactions, so I should have 2 terms. I'm going to be adding those 2 terms up, okay, to get the overall rate of change, right? Because right, we think about this, right? The concentration of B, oh my gosh, this is not plus, this is going to be, right? Okay, that makes more sense. Right, 2A going to B, and then B plus D going to P. All right, that makes a lot more sense. Right, so anyways, right. So again, in that first reaction, because B appears in that reaction, its concentration is going to be affected as the reaction's going, right? So in that first reaction, B is going to increase its concentration over time as the reaction goes, right? And then the second reaction, B is a reactant, so its concentration is going to be decreased over time because of that reaction, right? So both of those reactions affect the overall concentration of B. So that's why they both appear in this equation here, right? I'm asking how is the concentration of B changing with time, right? Well, it changes with time based off of how fast these 2 reactions go, right? The formation of B as a function of time is just related with the rate of that first reaction, right? That first reaction has some rate, okay? So V here I'm using for the rate of the first reaction, right? So the first reaction, right, I'm calling it as a reaction rate V1, right? Okay. And then for the second reaction, right, it has a reaction rate of V2, right? I'm going to call it V2, right? And so again, dB dt, okay, it's equal to V1 because it's getting formed in that first reaction. Okay, so I'm going to have a term that is related with an increase in my concentration of B as a function of time, which is it's increasing as fast as that reaction is taking place. right? So that's why I write V1. And then for the second reaction, it's a reactant. And so I'm going to put minus V2 because it's being consumed in that second reaction, right? It's concentrate, right? Reaction rates are always positive numbers, right? The rate of reaction is always a positive quantity. And so if I have, right, so that means that I should be subtracting off the rate in which reaction 2 is taking place, right? How fast is reaction 2 taking place? Well, my concentration of B is being reduced by that speed, right? And so now what I can do is these are elementary reactions. So now I can write out what does V1 equal in terms of concentrations of things, right? What is the rate law for reaction 1? Well, reaction 1 is an elementary step, right? So the rate law is just equal to the rate constant, K1, times concentration of reactants, which is A times A, or A squared, right? And the second one, I have this minus sign now, right? The rate law for my second reaction is just K2 times the concentration of B times concentration of D. Okay? Right? And that is the answer to what's being asked, right? We're just asked, how does the concentration of B change over time? Well, it changes according to this equation. Okay? K1 A squared minus K2 B times D. Okay? Now, this isn't a great equation, and it's not very nice, and we would, if we were trying to do certain things, we'd go beyond this, but in terms of what was asked in this problem, that's what was asked, and that's our answer, right? So this is what we have. Okay? So questions about how I got to this final answer, okay? Because this is something you're going to do a lot for the rest of kinetics, okay? So get used to it, get comfortable with it, be friends with it, right? Get familiar, cozy on up, whatever other terms you want me to use, right? So any questions about this? About what I did, how I did it, why I did it? Okay. All right, so I'm going to ask you to do a similar thing. And I want to ask you, what is A dt equal to? Okay. So take a second. I got, so if it's the same mechanism, I'm just asking for what is dA dt equal to. Okay. So take a minute. Just write that out. All right. So what do people think this is? dA dt will equal what?
Figured since it's only in the first term or the first mechanism, that you only have to consider that rate constant.
Hold on a second. For those who are on Zoom, I need to crank up the volume here because I can't hear a word of what you're saying. All right, try that again.
I just said I figured since you only see A in the first reaction mechanism, that you are only going to consider that rate constant. And it wouldn't be like the sum of both rate constants.
Yeah, right, so since it's appearing in just this first reaction, there's only going to be one term, right? And so yeah, so it's minus K1 times
Is it just A squared?
A squared. Does that seem good to everybody? Okay. Well, you're all wrong. Ah, ha ha ha. I tricked you. Right, we got to, so why I wrote things out like this is, remember, okay, for this reaction, okay, V1, right, which happens to equal minus, trying to do this where you can see the whole thing, right? So minus K1 A squared, right? Right, that's true, or not minus, sorry, it's just equal to, right, V1 equals K1 A squared. Ugh. Square out, right? That's what V1 is, right? The rate law for reaction 1 is just K1 A squared. Everyone's got that down. Great, right? And then you are correct that the change in concentration of A is going to be minus that rate law. But remember, I have to divide by the stoichiometric coefficient, right? So dA dt times minus 1/2 is what equals that rate law, or what equals the rate of that reaction, right? And so this is going to be multiplied by a factor of 2. So it's going to be negative 2 K1 A squared, right? Because again, the rate, right, this reaction 2A going to B takes place, has some speed, right? Let's say the reaction rate is 1 mole per minute, right? Let's say that's what my reaction rate is, right? 1 mole per minute, okay? Well, the change in concentration of A is going to be 2 moles per minute, right? Because for the extent of my reaction proceeding by 1 mole per minute, the A has to decrease by 2 because I'm consuming 2 A's for every time this reaction is going, right? And so the rate of change of A is going to be twice as fast as the rate of the reaction, okay? Because of its stoichiometric coefficient there. And so that's why I get 2 times K1 A squared, okay? But notice here that there isn't a factor of 2 that appears here. And that's because the stoichiometric coefficient of B in this reaction is just equal to 1, okay? So you need to care about the stoichiometric coefficients and whether or not you multiply by them when you're concerned with the rate of change of A. Well, it has a stoichiometric coefficient of 2, so that 2's got to appear there, okay? But that stoichiometric coefficient of 2 always appears as a squared, right, in the rate law. So it's kind of an annoying little thing, right, that these stoichiometric coefficients, when writing out these equations, okay, appear as, exponents and multiplicative factors, kind of depending on what you're doing, right? It's always exponents in the rate law. But whether or not you multiply by 2 depends on, are you talking about the change in concentration of A? Well, in that case, yeah, you need to multiply it by 2 because the change in concentration of A is twice as fast as the rate of that reaction, okay, based off its stoichiometric coefficient, right? While the change concentration of B is equally as fast as the rate of the reaction because of its stoichiometric coefficient of 1. Okay. So yeah, so that's so I wanted to do this second kind of question here, the second example here to kind of hammer home that point that, right, because, right, the rate of change of A times minus 1/2 is equal to the rate of the reaction, right? I have this factor of 2 appearing there, right? And so that's just something, right, to keep in mind, right, so that we don't forget those factors of 2, which can often be a common thing to do. Okay? So questions about that? Questions about the problem? Why I have a factor of 2 in the second expression and not in the change concentration of A and not the change concentration of B? Why is there only one term? Anything? All right, again, right? Again, get very comfortable, get very familiar with doing these things, okay? Because we're gonna have mechanisms that are gonna have like 5 elementary steps and something's gonna appear in 4 of them or something like that, or maybe all 5, right? And you're gonna have a big long set of equations and things like that. And basically, right, all of what we're doing for kind of the rest of the kinetics when we're talking about these mechanisms and stuff like that, for the most part, is all just a bunch of algebra. That we're going to have a bunch of linear equations, and we got to solve for some variable, right? Going back to your days of algebra, whenever you took it, right? You got like, two equations with x and y, and you got to find out what is x equal and what is y equal, right? Two equations, two unknowns. We're going to have wonderful things with that, with three equations and three unknowns, or two equations and two unknowns, or whatever, so we're going to have lots of fun solving for unknowns and things like that. Or at least I think so, but probably you won't. We'll see. All right. So let's go back to the slides here then. Okay. So again, right, just writing out the first reaction, right, the change in concentration of B is related with the rate of the reaction, which has that rate law of Ka squared, and then it also appears in second reaction, minus, right, so the total is just the sum of those two things, right? So, oh, and that's the exact same slide after, right? Right, and so if we have, so here is an example. I wish I had not done something. Yeah, that was literally the same. Okay. So I kind of gave some of the punchlines here, but often you might see mechanisms written like this, where you have one of the elementary steps is an equilibrium step, where it can go in the forward reaction and the reverse reaction. Okay, so it's written like that just to kind of, make things a little bit simpler in terms of how many equations and things like that you have to write, right? But technically, this mechanism has three reactions. It has 2A going to B with the rate constant K1. It has B going to 2A with the rate constant of K minus 1. And it has B plus D going to P with the rate constant of K2. Okay? So whenever you see an equilibrium arrow, that's adding an extra reaction, right? And that's why there's an extra rate constant written to the side of that reaction, right? K1 is for the forward reaction, 2A going to B. K minus 1 is for the reverse reaction, B going to 2A, right? But those are two different reactions. And so again, this mechanism has a total of three reactions, and B appears in all three. And so that's why for the change of concentration of B, oh yeah, this is some wonderful typos, and I forgot the squares here. Let's fix that real quick. All right. Yeah. Okay. Right. And so that's why for the change of concentration of B as a function of time, right, I have three terms, right? That first term is how B is being consumed in the reverse reaction with the rate, right? The rate of that reaction, right, has a rate law of K minus 1 times concentration B. So that's how I get this minus K minus 1 B, right? Then it appears in the forward reaction, and that first reaction, that equilibrium reaction, which is again K1 A squared, okay? And then it appears right in the second reaction, which is minus K2 BD, okay, for that rate law, okay? But again, you can go back and think of these things how I did, and I'll do this often as well, because it can help kind of simplify things down, right? So it doesn't hurt to write things out like this initially, okay? Like if I were to do the same thing for this question here for dA dt, what I would have written is I would have put dA dt is equal to minus 2 V1, okay? I would have said dA dt is minus 2 V1. I would have said, okay, V1 is equal to K1 A squared and plug that in, okay, to get this, right? So doing kind of this steps with writing the rate of change in terms of the rate of reactions doesn't hurt, right? And then you could write, okay, up top, V1 is equal to K1 A squared, right? V2 is equal to K2 B D, right? So you could do something like that, right? And you have this written down, have these two equations written down, okay, and then plug in for what V1 and V2 are to get the final equations. Okay, so sometimes on slides and things, I'll kind of do that all in one step, but it also sometimes can bring some clarity, especially with more complicated mechanisms. If sometimes you write things out in terms of V1s and V2s and stuff, so you don't have, right? So this second equation here, dB dt equaling all this stuff, right? This can look a little bit more simpler if I just write minus V minus 1 plus V1 minus V2, right? Instead of concentration to B, A squared to B and D and blah, blah, right? So sometimes things can look a little bit more simpler, and how to solve certain problems might be more clear if you write things out like that. You don't have to and whatnot, but you know, it doesn't hurt to, you know, in terms of making sure you've counted everything and making sure you got everything right and written out properly. So any questions about how I got the change in concentrations of A, B, D, and P for this mechanism? Okay. Note here again for A, because it has a stoichiometric coefficient of 2 in this reaction, okay, in both a forward and a reverse reaction, I have to multiply the rate of those reactions by 2 to get the rate of change of A. Okay. Any questions? All right. So a note about equilibrium reactions, okay? So if that reaction to A going to B is at equilibrium, okay, that does not mean, right, the rate constants are the same. It does not mean K1 equals K minus 1, right? Again, in equilibrium says the rate of the forward reaction equals the rate of the reverse reaction. So if this first reaction is at equilibrium, it's saying V forward, V1 equals V reverse, V minus 1, right? V forward is K1A, right? A squared. This slide I left off A squared as well. Fantastic. Right. Over here. All right, great. Okay. All right, so that V4 is K1A squared, V reverse, right, K minus 1B, right? And those, if the reactions at equilibrium, those equal each other. So we get K1A squared equals K minus 1B, right? Put the rate constants on the same side, right? And you get K1 divided by K minus 1 equals B divided by A squared. Then if I look at that equilibrium reaction and ask you, right, I have this equilibrium reaction, 2A going to B. What's the equilibrium constant, right? You'd say, oh, the equilibrium constant equals concentration of B over the concentration of A squared, right? And hey, that's what we have, right? And so what that kind of shows us, right, is that for an equilibrium reaction, that equilibrium constant is equal to the ratio of the forward rate constant and the reverse rate constant, okay, right? Oh, shoot. One last place I forgot the A squared here. Right. And again, that's what is being said. If the reaction's at equilibrium, right, it's just saying that this equation is satisfied, right, or this equation, if you have the equilibrium constant, right, K is equal to B over A squared, right? This is being satisfied because the reaction's at equilibrium, okay? Not that K1 equals K minus 1 or anything else like that. Okay? Questions about this? All right. So now what we're going to do, we'll see if it's for the rest of the class or not, is we're going to go through in a little bit more detail how to get the actual concentration as a function of time for the reactant, intermediate, and product for the simple mechanism. A going to I going to P. Okay? Very simple mechanism, 2 reactions, 1 reactant, 1 intermediate, 1 product, right? Can't get much simpler than this besides just having, I guess, 1 reaction, right? Okay, so for this mechanism, right, we're going to try to answer the question, what is the concentration of P as a function of time, I and A? Okay, we're going to go through and derive that, and what we'll do in the next lecture is show, okay, you know, we can do this exactly for this simple mechanism, but it's not easy. And here's some approximations we can make, and what do those mean in terms of kind of what we derived here and things like that, just to give us a little bit more clarity and whatnot in terms of what does the steady state approximation mean? What does the pre-equilibrium or rate determining step approximations mean? Okay. We'll write that back to kind of this simple mechanism here. All right. So right, we have the simple mechanism. We can write out the change in concentration of A, I, and PR for this mechanism. Okay. Right. Just with how we talked about doing those things, right? Okay. So any questions about where those 3 equations at the bottom of the slide came from? How got them?
Could you explain again why the change in the concentration of A over the change in time is negative?
Yeah, because A in that first reaction is a reactant. So its concentration is going to be decreasing over time. And so, yeah, so that's why there's a minus sign. So basically any time, you know, if I'm looking to write these things out, right, I see A here only appears in the first equation. So I know there's only going to be 1 term for dA dt. Okay, so dA dt only has 1 term because it only appears in 1 reaction. In that reaction, it is a reactant, right? Which means that it's going to be decreasing over time, so it's got to have a negative in front of it, right? Because Ka is just a rate constant, a positive number. Concentrations are always positive numbers, right? You can't have a negative concentration. That makes no physical sense, right? So that's always a positive number, right? And so we know the concentration of A is always decreasing over time because it's a reactant. And so it has to be negative Ka times concentration of A. So, yeah, so that's where that minus sign comes from. Similarly, right, for I appears in both reactions. So there will be 2 terms. In the first reaction, it's a product. So it will be positive times that rate law, which is Ka times A for that first reaction. And in the second reaction, it's a reactant. So it's going to be negative of the rate law of the second reaction, which the rate law of the second reaction is KBI. So that's how I get that minus KBI.
Okay, thank you.
Mm-hmm. Any other questions? Yeah. Again, these are good questions to ask. Okay, because like I said, right now we're doing this for some simple mechanisms, you know, 1 or 2, you know, 2, maybe 3 reactions, you know, very few products, intermediates and things like that. But eventually we're going to start doing this for more complicated mechanisms. And there's going to be a lot more terms and a lot more stuff. And so it'll be a lot. Yeah. And so if you're not comfortable with kind of writing these things out right now, it's only going to get worse. So again, please make sure to ask plenty of questions to make sure you kind of understand how we got what we got on these slides. Okay. All right. Okay. So, right. So I have these differential equations. I want to try to solve them basically in order to get the concentration of A, I, and P as a function of time. Okay. Well, for the equation for A, right, this is just our simple first order kinetics problem, right, which has an integrated rate law of concentration of A is just equal to the initial concentration times E to the minus KAT, right? So we can do that pretty simple, pretty easily, right? Because again, we know what the concentration of A is. We can solve for what the concentration of A is as a function of time based off of that differential equation, right? Which is again, this differential equation is our first order, right? Kinetics problem, first order rate law. Yeah, it's an integrated first order rate law. Okay. And now we have this equation for I, right? Let's start with I, right? After we get to A, well, I can plug in for what the concentration of A is as a function of time to get this differential equation here. di dt equals Ka times the initial concentration A naught times e to the minus KAT minus KB concentration of I. Okay. Well, this equation is a linear differential equation, okay, that has a solution that is given on this slide that you do not need to know how to get the solution. Okay, if you haven't taken differential equations or things like that, have no idea how to solve that, that's fine. You'll never have to solve this in this class ever. This is the only time we're going through and doing this type of an example, and we're doing it here in class, right? So we just need to, right, what we're really concerned about is the final punchline of these things and some other stuff. So don't worry about solving that differential equation, okay? But just note, right, that I can plug in for what the concentration of A is, get this equation here, and it has these solutions, right? So just take my word for it that this is the solution to that equation. That concentration of I is equal to the initial concentration of A times Ka over Kb minus Ka times e to the minus KAT minus e to the minus KBT. Okay, so that is the solution to this differential equation. Okay. Right. So finally, I can plug. I can use. So I could take, right, if I wanted to, I could say, okay, well, I have the concentration of I as a function of time. I can plug that into here. Then I can integrate that whole thing out, right, to get the concentration of P as a function of time. And you could do that, and you'll get the same answer as what I get here. What I'm going to use is the fact that the concentration of A plus the concentration of I plus the concentration of B always has to add up to the initial concentration. This is conservation of mass, right? Conservation of matter, right? Because everything has a stoichiometric coefficient of 1 in this reaction mechanism, every 1 mole of A I lose, I'm forming either 1 mole of I or 1 mole of P, or some combination of moles of I and P that sum up to be 1, right? So the total number of moles in this reaction as it's going place doesn't change ever, okay? Because the stoichiometric coefficients of everything here is just 1, and each reaction is not creating or destroying some total number of molecules, right? So because of that, right, this reaction, the total concentration, right, is always equal to the initial. And so I can just add those things up. I already solved for what I is. I already solved for what A is, right? And then I can solve for P, right? So plugging in for what the concentration of A is as a function of time, concentration of I is a function of time, and rearranging it, you get this equation here, which simplifies down to this equation here. Okay? So the final concentration of P as a function of time is the initial concentration of A times 1 plus Kb e to the minus Kbt minus Ka e to the minus Kat divided by Kb minus Kb. Okay? So questions about this? Again, we're not going to do something like this on homework or on exam, but again, we're going to kind of do this, right? So we can kind of talk about, okay, what do those things look like, right? And say, okay, well, right, A just has the exponential decay, right? So you get this lovely, right, start off with some concentration of A and just decays exponentially, right? I has some growth and then it decays down, right? And then P is just continuous kind of growth that's somewhat exponential. Okay? Right? And you could, change what Ka and Kb is, and that will affect what these curves look like. We'll talk more about that with steady state approximation. Okay? So again, the point of going through this, getting these equations, will be is to kind of emphasize, this very simple mechanism, right? A going to I going to P, right? Solving for the concentrations of these things as a function of time is not easy, right? It can be done analytically for the simple mechanism, but it's not going to be able to be done in general for more complicated mechanisms, okay? And so in order to get some type of answer for things, okay, we're going to have to use approximations in some way, right? Because we're just not going to be able to answer them and solve for things exactly, okay? And again, and so, right, we'll again, when we talk about the steady state approximation, we'll kind of revisit this and talk about what does the steady state approximation mean in terms of what kind of stuff we've shown here, right? When does it work? When is it valid? When is it not? And things like that, okay? All right, so consider the following reaction mechanism. The rate of the reverse reaction for the elementary step 1 is equal to what? The rate law, I should say, right? So the rate, I should kind of say the rate law. But the rate law for that is equal to what?
The B.
B here? Yeah, it is going to be B K1 minus, sorry, K minus 1 P. Okay. That's it. So it's B here, right? K minus 1 P. A is the rate law for the forward reaction. C is the rate law for the second reaction. And so, yeah, so B here. All right. So here, consider the above elementary step, which is one of 6 steps in a reaction mechanism. Okay. So we just know it's one of 6 steps. We don't know what step or things like that. Which of the following statements is not always correct? So is A, the forward rate is V1 equals K1 AB. Is that always correct or not always correct? If it's not always correct, right, the answer would be A. B is not always correct, it would be answer B, right? C, the reverse reaction is unimolecular. D, A is reactant in the overall reaction. E, none. All 4 are always correct. Or F, more than one of these is not always correct. I'm hearing D, A, E, D. Okay. Yeah. So D is correct, right? It's a correct answer, and it's not always correct, right? Okay. Because again, we're just told A plus B going to C is one of 6 steps. But we don't know which step in the mechanism. We don't know the other steps, so we don't know if A is an intermediate. Maybe A is a catalyst, right? And so, yeah, so it'd be D here. A is a reactant in the overall reaction. That's not always true. It could be true, but it's not always true, okay? The reverse reaction, C going to B plus A, is unimolecular, right? And then A and B, those are the rate laws for those 2 reactions, and those are always true. Those are always going to be the rate laws, no matter what step in this mechanism this elementary step is, okay? So here, right, I have a question of, I have this mechanism. The question here is identify the incorrect rate expression based on that above mechanism, right? So is dA2 dt equal to minus K1A2 plus K minus 1A squared? If it's not, then that's incorrect, right? Blah, 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 blah. And then the question, and then G is all 6 expressions are correct, or H, more than one of them is incorrect. So we got someone saying B is wrong. Class here. So we got some people in the chat. H, E, and F incorrect. Okay.
B is the only one I'm not confident on. If I was, I would say B.
All right. So, all right. So let's look at some of these. We'll start with like C through F because those are a little bit simpler, right? Right. So we'll work our way up from F, right? So F here we have dAc dt equaling K3 concentration of A concentration of C, right? Well, if I'm looking at what is the change in concentration of AC as a function of time, right? AC, the molecule AC only appears in that third reaction, and it appears as a product. So its concentration is going to be increasing as a function of time, right? And it's going to be increasing at the rate equal to the rate of that reaction 3, right? Reaction 3 here, which has a rate law of K3 times concentration of A times concentration of C, which is what we have for F, right? F dAc dt equals K3AC. That is correct. That is the expression for that. Okay? And then the same thing for AB here, right? AB only appears in the second reaction, which has a rate law of K2 times concentration of A times concentration of B. Okay. And because it has a stoichiometric coefficient of 1 here, right, it's just 1 times the rate of that reaction, which is K2AB. So E is correct as well. Okay. And then D here, we have C, what we're looking at, change of concentration of C as a function of time. Well, C is a reactant only in that third reaction. So its concentration's got to decrease as time's going on. So my change of concentration of C is going to be minus the rate of that third reaction, which the rate law for that third reaction is K3, concentration of A times concentration of C. So D here is correct. Answer C here, right, dB dt equaling minus K2AB, okay? Well, we see B only appears in the second reaction. It is a reactant, so it should have a negative sign, and the rate law for that reaction is, in fact, K2AB. So C is also correct. So far, we've seen that F, E, D, and C are all correct. I'm going to jump to A because that's the next kind of simplest one, okay? So, right, answer A, D, A2 dt, right? So the change of A appears in only the first reaction, but the first reaction is an equilibrium reaction, so there's going to be 2 terms. There's going to be a term for the forward reaction and a term for the reverse, right? In the forward reaction, A2 is a reactant, right? So it's going to be minus the rate of that forward reaction, which is K1A2. So minus K1A2 for the forward reaction. For the reverse reaction, A2 is a product, so it's going to be a positive K minus 1A squared, okay? Because the rate law for the reverse reaction is K minus 1A squared, okay? So A is correct as well, okay? And so finally, let's look at answer B here, dA dt, okay? Well, A appears in every one of these reactions, okay? So it's got to have 4 terms. Luckily here, I got 4 terms, so that's at least a good sign, right? In the third reaction, in the second reaction, it's a reactant. So it has, right, its concentration is decreasing as the rate of that reaction is occurring. So it's going to be minus K3AC and minus K2AB for reaction 3 and reaction 2. So that's fine. So now it's for the equilibrium reaction, right? Well, an equilibrium reaction is being formed in the first reaction, right, in the forward reaction. And it's getting formed at a rate of K1A2, so that's fine. But I'm forming 2A, right? So the rate of this is actually 2 times K1A2. And then for the second term as well, right, the rate of change of A here is twice the rate of the reaction, which the rate of the reaction is K minus 1A squared. So it's going to be minus 2 K minus 1A squared. So B is incorrect just because we're missing the factors of 2 in those first 2 expressions. So B should be 2K1A2 minus 2K minus 1A squared, and then minus K2AB minus K3 AC. Okay. So B is the only one that's incorrect, and it's only incorrect because it's missing a factor of 2 in 2 of those terms. So questions about this, about getting A through F. This is a very good example of a mechanism, that's closer to some of the ones we might be looking at. It has a total of 4 reactions going on, right? And one of these things happens to appear in all 4, right? Okay. And A here is that intermediate that appears in all 4, right? And so, this can easily be a common thing that could appear for the rate of an overall reaction, okay? Or rate mechanism and things like that, right? And so this is a very good example of kind of these rate of changes that you might need to write out, okay? Because if I want to solve for the rate law for this, for the overall, right? The overall chemical reaction here is A2 plus B plus C going to AB plus AC, right? That's the overall chemical reaction, okay? If I want to write the rate law for that overall chemical reaction, I'm going to need to write out at least some of these things. I might not need to write out A through F, okay? You're not going to have to write out A through F to solve for that, but you might have to write out some of these rates of changes, okay, in order to solve for what the rate law is for this mechanism. Right. And we're not able to solve for that rate law as given. We're going to have to use some approximations, and we'll, again, talk about those starting next week when we talk about the steady state approximation and the pre-equilibrium approximation. Okay. But yeah, so questions about this example, about how B is not the right, B is the correct answer because it's not correct, right? Really. Should have thought about how I kind of phrase and write out these things. But yeah, right. B, the equation for B is incorrect, and so that is the correct answer to the question, right? But yeah, so any questions about that, about this example here? Again, we should, I'm spending plenty of time talking about this and asking if there's questions, going over this, because I really want to make sure we're all on the same page with this lecture, and they're all doing fine here with the material in this lecture and how to write these rate of changes from these elementary steps in reaction mechanisms, okay? Because you're going to do a lot of this, right? And so, if we struggle with this part, then we're not going to be able to do kind of the next steps of solving for the actual rate law. Okay. So if you can't write out these things correct, you'll get incorrect rate law every time, right? So we need to be able to write out these rate of changes correctly first before we can solve for the rate law. Okay. So I know it feels like I'm beating a dead horse as the expression goes. A horrible expression, but yeah. I don't want to, keep on jumping ahead and start doing like steady state approximation and things like that. I want to leave all of that for Monday because we'll have plenty of examples to use the steady state approximation on and then go over that, and we'll see lots of that. So we'll end this here today, but there's plenty of time that if people are like, I really don't feel comfortable doing this stuff, I'm happy to go over another example of writing out these rate of changes from a given mechanism and stuff like that. But otherwise, that will be it for today. And then, people are welcome to leave if they'd like. But I will stick around if people have questions and want to go over things. Yeah.
In the kind of order of just kind of setting it up, you stated before, so just kind of talk out B instead of do a bunch of work. It'd be like V1 minus V1 squared, or that two that's just part of the variable. I don't need to worry about negative V1.
Yeah. So when doing so kind of the question is right, and again, if people in the classroom or on Zoom feel great about this stuff. You want to leave, that's fine. But if you want to stick around for the question, you're welcome to, right? So let me write out, I kind of remember the mechanism, right? So if I wanted to do what is dA dt, okay, right? If I want to write in terms of v, right? I know it appears 4 times, so I know I got 4 terms, right?
Yeah.
So I got to add up, okay, right? And it's a product in the first one, so it's going to be V1, okay? And then it's a reactant in the second one, in the reverse reaction, so it's going to be negative V minus 1.
Yep.
Then it's a reactant in V2 and a reactant in V3, okay?
Beautiful.
So you have that, but remember for this, it had the stoichiometric coefficient, right? It was A2 going to 2A, right? So because that stoichiometric coefficient of 2, for these first 2, I have a factor of 2 that I got to multiply by.
So much. Okay.
Yeah.
Yes, sir.
Right. And then I can plug in the fact that, okay, V1 is just K1A2, right? Or A2, right? I can plug that into there, and I can plug in V minus 1 is K minus 1 A squared, right? And I can plug that into there, and so on and so forth, right? But yeah,
Yes, sir.
but I will be doing this a lot myself as we're working through more examples. Oh, sorry. As we're working through more examples in class and such next week. I'll write out things like this a lot as well, because it really does just make things a little bit simpler than starting off and writing out,
It's almost
all of this stuff
It's
at
almost
once.
a check for your coefficients. I wasn't trying to interrupt
Yeah.
you, but like I'm just trying to get the thought process there, and that makes more sense.
Yep.
That's almost another way to keep you from making mistakes.
Yeah, right.
Yes, sir.
Yeah, so the coefficients pop up. Yeah, that's a good way to think about it, right? The stoichiometric coefficients in your reactions always appear in the rate law as the exponents, right?
Mhm.
Right. If I stoichiometric coefficient 2, I always get a factor of 2 here, right? But in terms of the stoichiometric coefficients appearing as multiplicative factors, right? It only matters when I'm looking at A and it has a stoichiometric coefficient of 2 in the reaction, right? Again, when I looked at dA2 dt, right, it was just minus V1 plus V minus 1, right? With no stoichiometric coefficients of 2, because A2 had a stoichiometric coefficient of 1 in this reaction, so it never needed to be multiplied, right? So yeah, so that's also a good way to keep in track. When does that stoichiometric coefficient appear as a multiplicative factor versus an exponent, right? And again, always will be in the exponents in your rate law expressions, but might not always appear as a multiplicative factor depending on this stuff. Yep. Other questions? All right, so I will see you guys on Monday. We'll start doing the steady state approximation. Basically, be doing the steady state approximation until we finish kinetics.